Dear all, I'm Li Zhenyang from State Key Lab of CED and CG, Zhejiang University. Now I'm presenting our work entitled Deep Learning with Attention Mechanism for Electromagnetic Inverse Scattering. The other authors are Dr. Han Wang, Mingjie Pang, Yan Kaijiang, and Professor Hai Lin. Thanks so much for allowing us to do this presentation in this way online. I will show in the following 4 parts. The first one is introduction, including background and motivation. We call inverse scattering problems as ISPs. And what is it? Firstly, in forward scattering problems, the properties of scatterer are known, and the goal is to calculate the scattered fields. However, in inverse scattering problems, the scattered fields are known by measurement, and the goal is to determine the shape, position, and material of the scatterer from the measured scattered fields. Due to its highly nonlinear and ill-posed properties, solving ISPs is a challenging task. Traditional iterative method has been applied for solving ISPs. However, their expensive computational cost limits their application in practical engineering. In recent years, deep learning has shown success in imaging processing. The essence of deep learning is to obtain a nonlinear map between the input and desired output, which is very suitable for solving ISPs. And the trained neural networks can solve typical ISPs in real time. But the main drawbacks of traditional deep learning is the lack of physical knowledge, implying that unnecessary training costs will be wasted on important and unimportant information. To solve this issue, the biggest challenge is how to inject physical knowledge into deep learning networks. These pictures shows that different features have different corresponding attention masks, and attention mechanism can automatically assign weights to make the neural network pay more attention to important information. So the attention mechanism can extract the important physical related information from the measured scattered field matrix. In this paper, a new technique is proposed by introducing the attention mechanism to U-Net. The second part is formulation. The two-dimensional electromagnetic ISPs in free space shown in Figure 1. The unknown target is located in the investigation domain and illuminated by the incident with E incident. The scattered field excited by each illumination is received by M receivers. The measured scattered matrix can be described by this one. For the N transmitter, the incident field and the scatter field can be governed by these two equations, where Rm equals to xy denotes the coordinates of the point. This one represents the total electrical field, and G is the 2D Green's function in free space. Finally, epsilon r is the relative primitive to be solved, which can be solved by this one. E scatter is the measured scattered fields, and this one is the calculated scattered field when the relative primitive equals to epsilon r. T is the regularization used to balance in data fitting, and alpha is a constant. The traditional U-Net takes the measured scatter field matrix as input and convolutes it directly. Since the measured scatter field matrix is a 3-dimensional complex matrix, the information it contains is very complicated. The traditional U-Net faced the problem of slow training speed and low accuracy. To alleviate this problem, we propose a U-Net with attention mechanisms which can automatically avoid the computational cost for unimportant information. We add an attention gate composed of a 1 times 1 times 1 convolutional kernel and sigmoid function to each layer. The diagram is shown in figure 2. The third part is numeric result. Parameter settings of simulation results. In a 2 meters times 2 meters investigation regions, there are 128 transmitters and 128 receivers evenly placed on a circle with the ratios of 3 meters. The investigation region and the circle are centered at 0, 0. A dataset of size 800 is prepared for the ISP within the investigation region at 400 MHz. The dataset comprises the composed objects with uniformly distributed position within the investigation region and normally distributed primitive ranging from 1, 0 to 1.8. We use 560 sites in the dataset at the training site and the remaining 340 sites at the test site. In addition, we set the mean square error at the loss function. We compare the proposed method with the traditional UNet and the same parameter settings. Figure 3 shows that the proposed method have a better performance than the traditional UNet in terms of training speed and accuracy. The reconstruction result in figure 4 illustrates that the proposed method has a good performance on both geometric and physical properties. The last part is conclusion, including concluding and future works. In this paper, a deep learning technique combining the UNet with the attention mechanism is proposed to solve the ISPs. Because the attention mechanism can automatically avoid the computational costs for unimportant information, the proposed method has shown improved accuracy and efficiency compared to the traditional UNet. However, the attentional mechanism is still a black box algorithm with explained physics knowledge application. In future, we will concentrate on address this issue to incorporate domain knowledge into our models. That's all. Thanks for your attention.